Hi, and this is the Physics High podcast. A quick quiz. Do you A, want to be inspired by science communicators? B, want to learn all about science education? C, want guidance on your scientific journey? Well, how about D, all of the above? Well, today my guest needs no introduction, particularly if you have any passing interest in physics, and in particular particle physics. He is a particle physicist and he's published over 1,000 papers on particle physics alone, who was responsible as part of a team in the discovery of the top quark in 1995. He was also part of the team that was responsible for the discovery of the Higgs Boson in 2012. He's now also become the face of Fermilab, producing many videos on physics topics ranging from particle physics to cosmology, interspersed with all the dad jokes. He's written books, articles, a regular contributor to the physics teacher, Forbes, and CNN. So my guest today is none other than Dr. Don Lincoln. Welcome, Don.
Well, thank you for inviting me. I'm looking forward to talking some physics.
Now, your job description in one of the websites I read was like, I'm going to quote you here. It says, I'm a particle physics researcher. I work on the LHC. I smash protons together and we'll see what comes out. That is all. Assuming that there are people who probably don't know of the full range of your expertise, do you want to elaborate a little bit more what you do?
Sure. So I am a senior scientist at Fermilab, which is America's flagship particle physics laboratory. And I split my research time between here and CERN, which is Europe's flagship particle physics laboratory. And we can debate on to which one, wins on that, but we all know. So what we do is, it depends. I mean, what I do is I use the Large Hadron Collider of late, where we collide beams of protons together at near the speed of light. So you have them traveling at basically 300,000 kilometers per second, traveling in two different directions. They collide together. And so everyone has heard of Einstein's E equals mc squared. People don't always completely understand what that means, but it says that energy can be converted into mass and mass into energy. And so one of the things that we do is by colliding these two particles together with incredible high energy, we can recreate the conditions of the universe a tenth of a trillionth of a second after the Big Bang, and we are able to look for matter that exists for less than a trillionth of a second and actually understand its properties. So what we're trying to do in big picture is to understand the ultimate rules of the universe, and what holds matter together, what makes what we see out there. Why are we here the way we are? In addition, we really are trying to recreate the conditions of the Big Bang, understand literally the moment of creation, how the universe went from whatever was before, and for that we have, that's another conversation, to the expanding, marvelous, majestic universe that we see now. So that's what I do.
Now, you've got some claim to fame too, of course. So in 1995, you were the discoverer, and I know that you weren't the only one. There was a team involved, but certainly your name is associated with the top quark, I guess the bigger brother of the up quark. So can you tell us a little bit more of how they came about, and in particular, what the process was in actually measuring that?
So, yes, I always tell my publishers that I discovered the top quark. Of course, this is in conjunction with 800 of my closest personal friends, and but don't tell my mom, because somehow she figures I did it myself, and well, you know how they are. So I was actually quite young when that happened. I had just finished my PhD only a year before, and I had joined the D0 experiment at Fermilab. So Fermilab, like most large collider experiments, or large accelerators, has two similar quality experiments around them. And on the Fermilab accelerator, which is the Tevatron, there was CDF and D0. So I was on D0. And there it was similar to what I do now, but rather than colliding beams of protons, we had beams of protons and another beam of antimatter protons, which is actually mind-blowing when you think about it. But we had the largest concentration of antimatter on the planet. And what we did there is, of course, same thing. We accelerated the particles, we collided them together, we converted the collision energy into top quarks. Now, the mass of the top quark is ridiculously high. The mass of a top quark is about 172 times heavier than a proton, and it lasts for a very short amount of time. So while we say that we discovered the top quark, and that's true, we never actually saw a top quark because the top quark decayed far more quickly than it did not have time to travel from the creation point into our detector. So what we had to do was we had to use ordinary, regular, run-of-the-mill high school physics. And that was what we did, because we know that energy is conserved and momentum is conserved. So if a top quark decays into two particles that live for a long period of time, you can measure their energy and their momentum, and then from that you can add them together, and then you know the energy and the momentum of the top quark itself. Now, it turns out that the top quark decays into three particles because it decays first into a bottom quark and a particle called a W boson. And a boson, that is it is the force-carrying particle of the weak force. And that is also a very heavy particle, and then it splits into two more particles. So a top quark goes actually into three particles, one of which is almost always a bottom quark. But since we made a top quark and an antimatter top quark together, then that means we had six particles coming out. And so you have to, when you think about that, the detector doesn't say these three particles go with the top quark and these three particles go with the other one. So you had to work out which ones went with one another. And so you do that by doing all the possible reasonable combinations. And what you do is you find that if you combine a specific three and another specific three, you end up finding out that they came from two particles with similar mass. And so that's one of the criteria. I mean, there's many criteria, but that's one of the criteria by deciding what the right combination is. And so we did this. Now, we've been looking for the top quark since like 1977. So the bottom quark was discovered at Fermilab in 1977. And by the time we knew enough about quarks that it seemed that quarks came in pairs. There was a 2/3 charge quark and a minus 1/3 charge quark, where the charge I'm talking about is the charge of a proton, or the minus is the charge of the electron. So we knew about the up and down quark. We had discovered in 1974 the charm quark, so we knew the charm and strange quark. When the bottom quark was discovered in 1977, we said, well, of course there's a top quark. However, nobody had any concept of just how much heavier the top quark was than the other particles. The bottom quark has a mass of about 4.5 billion electron volts, about, just if you call a billion electron volts the mass of a proton, which is close. So 4.5 times the mass of a proton. The top quark is 172 times the mass of the proton. So it took us a long time. So CDF was actually operating before D0 was, and they ran for some time and were unable to see the top quark. D0 came online in 1991. I graduated, got my PhD in 1994, so they'd been operating for a while. But when you first start operating, what you end up doing is you shake down your equipment. It's like a race car. If you take it to the racetrack, it doesn't do its absolute very best the first time around the track. You have to tune up how the engine runs. So by the time I got there, it had been reasonably tuned up. And so I started working on the experiment. I was involved in a number of things, detector development and so forth, and I was there to see the top quark be discovered, and it was amazing. It was truly, truly astonishing. And as you may be leading on, yeah, I've been part of two really interesting discoveries. But the top quark was, a good way. When you're a postdoc, you're just out of your PhD. It was a great place to be. It was terribly exciting.
So then in 2012, you made your way to CMS. I thought I'd wear the CMS shirt just to make sure we know where the allegiances lie. And then you got together with like 2,000 of your closest friends and were involved with the discovery of the Higgs boson. Now, obviously, the physics of the discovery of the Higgs boson is a similar process in terms of high school physics, of looking how the particles interact with the fields. But what was your role, particularly at CMS, and obviously the buzz of being in that room when they announced the results in 2012?
Well, you actually understated the number of people. When I say I discovered the Higgs boson, it was me and one of 6,000 people. So there are two experiments. There's CMS and Atlas, and I am grateful to see that you're wearing the right T-shirt. And both of the two experiments had about 3,000 people. So it is, any individual has necessarily a more modest connection to the discovery of such a big particle. At the time, I was involved with the operation and checking the data integrity of the energy measuring device on CMS. It's called a calorimeter for calories, and so we measure energy. There are two different devices, one that measures energy that's predominantly electromagnetic, so electrons and photons. And then there is another one called the hadronic calorimeter, which measures energy that is more like protons hitting the detector. It turns out it's a different particle called a pion, but to intents and purposes, it looks like a proton hitting the detector. And so my responsibility at that time was to have programs written that took all of the data coming off the detector, and it's a fire hose of information. It's truly astonishing. And what we had to do is simply establish that the detector elements worked. There's hundreds of millions of little individual detector elements, not all in the hadron calorimeter. The hadron calorimeter has a modest 60,000 detector elements, but every single one of those have to work, because what happens is, depending on the actual detector, you have particle deposits energy in the detector. It gives off a blink of light, or it gives off an electrical signal, and you don't have access to the energy of the particle. All you have access to is the electrical signal or the blink of light. So what you have to do is you have to establish that all of these 6,000 detector elements all give the same amount of electricity for the same amount of energy deposition, because otherwise you have no idea what you're doing. In addition, you have to establish that all of the detectors are working. I mean, if half of them are off and energy flows in that direction, you actually don't record that energy. So what I was doing at the time was being involved with establishing that the calorimeter was functional. So that was sort of my bigger piece from a hardware point of view. And part of that is simply by being older. So when you're older, the way the academic world works is you eventually have tenure. Your job is not in jeopardy. Whereas if you're a younger person, you don't have tenure, and you have to do something super incredibly exciting to make that transition for tenure. And so as a rule, what we try to do is we try to give the most visible, sexiest topics to the younger people, because it helps their career. And so at the time I had tenure, I mean, I was, well, of course, younger than I am now. So what they try to do there is they try to take expert people who have really, a lot of experience with things like either detectors or algorithms or computer operations, and they give them to some of the more senior people, because those jobs, when you say, oh, I made the detector work, that's not the same thing as I ran the program and here's the plot. And so we do try to give as much visibility to our young people as possible, because it helps their careers. So that's what we did. I mean, of course, we have senior people monitoring them and making sure that no mistakes are made. But anyways, that's what I was doing. And so the Higgs discovery was really pretty cool, because, again, that took a long time. I mean, that was proposed in 1964. So literally, when I was about, I don't know, 30 centimeters tall or something like that, is when the Higgs was proposed. And because of the enormous difficulty of manufacturing this, the need to have a lot of energy, a lot of intensity, it took essentially half a century to find the Higgs boson. And that was in itself another truly remarkable thing to be part of. In fact, it was probably even more exciting than the top quark, because the top quark, we'd seen things come in pairs. We saw that there was the up and down, and charm and strange, and top and bottom. If the top quark wasn't there, that would have been staggering. The Higgs boson was a proposal. We weren't sure that it worked. We knew that it agreed with some measurements that we had made. We knew that it was a plausible hypothesis, but until we actually had discovered the Higgs boson, there was always the very strong possibility that Peter Higgs was just wrong, and it would have been some other thing. And I have a book, one of my books called The Large Hadron Collider, where I talk a little bit about the history of the search for the Higgs boson. And because at Fermilab, we were looking, we did not find it, but we were able to slowly rule out places. We found out places where it didn't exist. And in sort of a weird irony, many of us were working both on Fermilab experiments and CERN experiments at the same time. So we were sort of competing with ourselves. And so we then, wearing my CERN hat, I beat me wearing my Fermilab hat. And so that's a very interesting story. And if you're really super interested in the history of Higgs, I absolutely strongly recommend a book by Ian Sample called Massive. It is a fantastic book. It is the history of the proposal of the Higgs boson, not just Peter Higgs, the other people that were involved, how they were involved. It's absolutely fantastic reading. If you like the history of science, you absolutely should read it.
Now, that's obviously now 9 years ago. What are you working on at the moment?
Well, I am working on a couple of things. Again, because I have experience in detector development, one of the things that we are doing is we are upgrading our energy. Well, we're upgrading many of our detectors, but I'm involved with upgrading our energy measuring detectors to use a completely different technology that should be much faster. And the reason is that and by we I mean all of CERN, all of the Large Hadron Collider industrial complex, for the lack of a better word, and the detectors, we are preparing for collision rates that are 10 times higher than we've done in the past. And so when you build a particle detector, it always just barely works. You know what the parameters need to be, and you build it to hit that. And the reason you don't build it to hit 10 times better is it's expensive. And furthermore, the technologies improve over time. And so if we were to build a detector, say 20 years ago, that could operate in this new environment that we're going to, which is 10 times to the interaction rate is 10 times faster than we have now, it would have used old technology, been more expensive, and been less effective. So we always build the detector just good enough. And but now we're upgrading everything, so we have to completely refurbish and upgrade the apparatus. So that's one thing I'm working on. From a physics point of view, the thing I do with the Large Hadron Collider data is I am just kind of fascinated by why there are what we call generations. So up and down quarks are what make up us. If you look in a proton or a neutron, there are up and down quarks. Up has a charge of 2/3, down quark has a charge of -1/3. But there's also the charm quark, which is the charge of 2/3, and the strange short quark has a charge of -1/3. So it's a carbon copy of the stuff that makes up us. But these particles are heavier, and they're unstable, and they decay. In addition, there is a third copy, and the third copy is the top and the bottom quark. So I am completely perplexed as to why there are these multiple copies when it's not necessary to make up the matter that we see around us. Now, I have a sneaking hypothesis, and by no means should anybody listening to me believe me. Do not believe what I'm saying, but this is sort of my mental thinking. If I put myself back in the mindset of a person in, say, 1900, and we looked at the periodic table of chemical elements, what we see is we saw that there are columns that are chemically similar. So hydrogen, lithium, sodium, potassium, they're all highly reactive elements. Or over on the other side, you have helium, neon, argon, krypton, xenon, and so forth, the non-reacting noble elements. So each column is pretty much the same. And as we go down through the column, they get heavier and heavier. Now, if you exist in 1900, you go, well, that's a very interesting pattern, but you don't know what it means at all. So in the sort of early 1920s, quantum mechanics sort of came into existence. We understood that electrons existed, and we now know that the chemical similarity has to do with the orbitals of the electrons surrounding them. So you have the 1s orbitals and the 2s orbitals. So if anybody has any chemistry, you know that the columns have to do with the configuration of electrons around them. In addition, the fact that they get heavier and heavier is because there are more protons and neutrons inside every element as you go down the columns. So we now have an explanation for why we see objects that are very similar and yet heavier and heavier. Well, this is sort of where we are with the quarks, except now the rows and the columns are interchanged, because we always write the columns, so you have an up quark, a charm quark, and a top quark. They're all similar, but they're heavier as you go from left to right. Now, I can't prove this, but it is very reminiscent of the periodic table of over 120 years ago, where we saw these repetitive structures, and they were hints of things that we didn't even understand for another 30 years. So I have this sneaky suspicion that maybe there are things actually inside quarks, and what we're seeing is either a top quark has more constituents, or the constituents inside the top quark is moving around faster, so there's more energy. Now, as I said, nobody should believe this. In fact, it is not a well-regarded theory among the scientific community, because we've looked for this, I've looked for this, and we have found exactly zero corroborating evidence. So it's now just a hypothesis by analogy to chemistry. But nobody should go away saying, aha, Lincoln's onto something, because if we were, I would have hoped that the LHC would have found it. What I find, though, as I even get older, I start taking back a bigger picture. I mean, things that I'm not working on, things like dark matter and dark energy, and just all of the mysteries that you see there are other LHC experiments that are finding measurements that don't hang together. Or recently at Fermilab, we had what we call the G-2 experiment, where we measured the spin properties of a muon to 12 digits of accuracy, and at 9 digits of accuracy, so 1 part per billion, they disagreed, which is amazing. So that means that the theory and the prediction agree to a part per billion. But when you get to past a part per billion, they disagree. And that could be the indication of new physics. So I find myself looking around at all these bright, shiny, interesting new physics results, hoping to see that one of them will just completely break our understanding and point our path forward.
You mentioned the healthy competition between Fermilab and CERN. It's obviously a healthy collaboration as well. So I have an acquaintance who I met at CERN, and she actually works for Fermilab, Claire Lee, who is based at CERN, but is working, she initially was at Brookhaven and then at Fermilab, and she's working on the Dune project. Are you having any interest in the Dune project? Because that's also a fairly new project for Fermilab too, isn't it?
It is a very new project. It's the Fermilab's future. It's the next 20 years. And what you find, I think, at Fermi is you get sort of two different mindsets. The people who like, the big colliders, the big camera that you can bash things with, and the people interested in neutrino physics. And I find myself more interested in the collider. But the Dune experiment is fascinating. So we already have the most powerful, most intense beam of neutrinos that we are currently shooting north of our laboratory to a state called Minnesota. But what we're doing is we're building an enormous facility 1,300 kilometers west of us, under the mountains of the Black Hills of South Dakota. So in a very different direction. And what we're going to do is we are shooting, or we are not shooting because we haven't built it yet, but we're in the process of building. We will shoot beams of neutrinos and antimatter neutrinos. And your viewers may or may not know, but neutrinos are mind-boggling, absolutely mind-boggling particles in that they change their identity. So if you start out with a neutrino of one variant, if you wait long enough, it changes to another variant. And that's just astonishing. It's as if a cat could change into a jaguar, change into a tiger, and then back into a cat again. And that's what it does. Now, one of the things that we're trying to do is to measure whether or not neutrinos and antimatter neutrinos change their identity at the same rate. And so you say, well, that's a fairly obscure thing to look at, but it really isn't, because the whole question of matter and antimatter is a huge mystery of modern physics. For instance, everyone's heard of E equals mc squared, and they may even know that this says that energy can make matter and matter can make energy. But when energy turns into matter, what happens is it actually makes matter and antimatter in equal quantities. So now when we take that information and we fold it in with the Big Bang, the universe was smaller, hotter, there was energy everywhere. Matter and antimatter should have been made in equal quantities. All of our measurements say that. And yet, what do we see? We look out into the universe, everywhere, all we see is matter. So something changed, something made the antimatter go away. And we don't know what that is, but there is a hypothesis, again, not proven, that's why we do the measurement, that perhaps the way in which matter and antimatter neutrinos change their identity is different. And if that's true, that might be a clue that tells us where all the antimatter went. So that's a sort of a background answer. I do not actually work on Dune, because you can work on one thing, or if you want to be effective, you can work on one thing. And I just picked the LHC because I kind of like it.
Now, moving on to your, let's say, your other alter ego, you have now produced over 100 videos. You've almost pretty much become the face of Fermilab with the YouTube channel for the last 10 years and gained a very large following as a result, and including on social media. What led to that?
So let me tell you a story. When people ask how scientists are made, it's hard to really know. I mean, kids are born curious, but that curiosity needs to be nurtured. And there are environments that are better or worse. I mean, some people are born to scientific families. My own children are, they have scientific parents, so they live in that bath. But I did not. I grew in what one might call charitably an academically impoverished household. My dad never finished high school, for instance. And my mom had me way, way too young. She eventually went on to be a nurse, but I was already a teenager by the time she did that. So, when I went home and I asked questions about dinosaurs or rocket ships or whatever, there really wasn't people to ask. But there were people like Carl Sagan and George Gamow and
Isaac Asimov.
Richard Feynman, and they all wrote stuff down that inspired and illuminated and fascinated some people, myself included. And so when I finally became a established scientist, basically I said, I got to pay this forward. I owe this to the people that came before me. So, and I found that I had some talent at writing. That's where I started. Very small things like magazine articles and books and so forth. And then I also found that I was a bit of a ham. If you look at my YouTube videos, some YouTube videos can be very stodgy. You get other YouTube videos where the person is, charming and debonair, and I'm, not sure I'm either of those, but I am really good ham and I tell bad dad jokes. And that seems to work pretty well. And so what I do is I try to take down the barriers of people who think, oh man, science, those guys are all so smart and so forth. But to see someone joking and explaining things. Now, a person seeing my video isn't going to go off and, become a scientist instantly, but they get a sense that, that's not so hard. Okay, yeah, I'm going to have to work to understand it really, but I understand it enough to know that that's really fascinating. And so that's what started. And then what I've sort of done over the years is try to learn about how the world of outreach and social media and media itself works. And it turns out that people like people. So when you talk about, science outreach, what you will hear is you will talk about Sean Carroll, you'll talk about Neil deGrasse Tyson, or Brian Greene, or unfortunately sometimes Michio Kaku, who I think does some dodgy things. And people start, they pick out these voices, or Lisa Randall, another one who's really very good at this. And so that's what the YouTube came from, is because that puts a face on things. Authors don't have a face, but YouTube does. And so, I've been slowly growing. I mean, it's not where I'd like to be. We passed 500,000 subscribers, but I really want to hit 1 million. But I think we got a few years before we get there. And so I write also now for CNN. I write for a magazine called Forbes. I have written things called the Great Courses. I'm not sure if you're familiar with them in Australia, but these are 12-hour video courses where I describe various things. And so I do each one of these, and they each reach a different demographic and a different market. I wish I could, be even broader, but, then you start getting yourself pulled pretty thin. I should add Instagram or TikTok, but I'm not cool enough for TikTok.
You were nurtured in some ways by the writers of the 70s and so forth. So you got yourself into university as a result, at Rice University, if I'm correct, and you then moved into particle physics. What made you want to move specifically in that direction?
Well, I've always been interested in what one might call the big existential questions, the questions of, what have historically been philosophical or even theological. How did we get here? Why is the universe the way it is? Does it have to be the way it is? And so I even studied, I have minor degrees in philosophy and religion because of my interest in these big, overarching, huge questions. But as I grew older, I came to realize that those disciplines, while science owes a great debt to them, those disciplines are not making the same kind of progress that science is. Now, there's a lot that science doesn't know, and I don't want to oversell it, but we now know how old the universe is, and we know how old the universe is to great accuracy. We know how big it is. We know the building blocks of the universe. These are things that sitting and philosophizing about are never going to tell you. But if you can actually break apart matter and look at it and understand the laws of it, you are that much closer to understanding these really enormous questions. Similarly, you look out into the universe, billions of light years away, you can see galaxies, the first galaxies forming, the first stars turning on. If you look even back further, you can see the cosmic microwave background radiation, something that happened a tiny fraction after a second, not a second, but a tiny fraction of the lifetime of the universe. And all of this we now know. And so this is why when I was young, it was a question of cosmology or particle physics. And when I went to graduate school in the mid-1980s, the technical capabilities of the cosmology community were not so developed. It was not so easy to do cosmology measurements. Nowadays, it's much easier. But the fact that we could the cosmology of the 1980s, there was more theorizing and less actual measuring. Whereas in particle physics, by God, you could take that accelerator, slam particle A into particle B, and you learn something real. So that's why I went the direction I did. Nowadays, I could have gone either way because cosmology is fascinating too. But it would have been one of those two. I mean, you aren't going to answer the big, enormous questions without digging deep, deep into the data under the harshest conditions possible and getting a sense of why we're here. And we're not there, and it's going to be a long time before we figure it out. But it's been fun being part of the journey.
My personal, I relate to you because my personal passions in physics have been the extremes. When I was at university, I took the extremes. So we had the quantum mechanics, the small stuff, and then cosmology, the astronomy stuff, or astrophysics stuff. And yet there's a synergy there too, right? Because when we're wanting to understand, let's say, dark matter, well, you need particle physics to try to maybe develop an understanding of dark matter, but it relates obviously to cosmological aspects too, and antimatter as well. So in many respects, they're two sides, but they meet in the middle in many ways.
Absolutely.
Yeah. You are as also a very effective science communicator. You've done TED Talks, you write articles. I read that it was a brief chat with Stephen Hawking that encouraged you to start writing books as well, of which you've produced multiple books and so forth as a result. And of course, we've already discussed your YouTube persona. Why is science communication important to you in terms of at the world at large?
First, and maybe even foremost, is, I think that there's some kid in the middle of Iowa or somewhere in the Australian outback, or for all I know, in Kazakhstan or something, who doesn't know that they like science. And so I think constantly having interesting things out there might set a spark. So that's a very important thing, and that's the large reason why I do it. But I guess I don't know how it is in Australia, but there's a large anti-science movement in the U.S. Anti-virus, anti-climate change, all sorts of stuff. Worries about the most recent telecommunication technologies, 5G, things like that. And this troubles me because I don't want policymakers making decisions about things that we know that are factually wrong. I mean, that's a dangerous thing. Now, one could argue perhaps a little bit about some of these things. We don't know everything about climate change, but we do know the climate is changing. We do know that humanity is part of that. What degree of it is, I don't know. And I don't think scientists should have the final answer. We shouldn't come in and say, oh, well, mankind is changing the climate, so we have to do whatever, windmills or nuclear power plants or not. Because that's a conversation for all of society. Everybody should have a voice at it. But by God, we should agree on the facts. Whatever we do, it might be, some idea might be too expensive, or it might be too dangerous, or it might be socially unacceptable for some other reason. That's a reasonable conversation. We can have that. But to say, no, climate change isn't happening, is just bonkers. And so this is why I really am, one of the reasons I'm incredibly passionate about science communication is let's just get the facts out there. And then we can have huge knockdown fight about what to do. But let's not say, oh, no, that's not real. Let's not believe that viruses cause autism, because they don't, that's crazy. And, there are people who will be mad at me for saying that, and I apologize to you guys. But there are things we know. There are things that science simply knows, things that science doesn't know. And, people just need to understand that. A case in point, we see this now in the States because of the worries about COVID. COVID came upon us relatively quickly. And it seems like the scientists were changing their mind fairly often. You should wear a mask. You shouldn't wear a mask. You should do this. You shouldn't do that. And people say, see, science doesn't know anything. But that's entirely the wrong point. The point is we were learning. We had an idea. We found out something and scientists said, oh, no, we were wrong. Scientists are the first people to say we were wrong because our goal is to be right. Not to win an argument, but to be right. And that means when we screw up, when we make a mistake, we need to change it and fix it. And so we saw this evolution in the recommendations, at least here in the US. And I like that people saw that. And I'd like them to take away the message, not that scientists don't know what they're doing, because we didn't know the answer in the beginning, but we kept working at it, getting it better and better and better. And so I think as long as scientists are honest about the strengths, the weaknesses, what science can and can't do, I want good science communicators trying to help humanity realize that once you start with a base of objective facts, that's the rock on which you can build any social policy. So this is important to me.
Am I correct to think that really, in terms of poor scientific literacy, there are those who are ignorant but are open, and that's who we're speaking to in terms of science communication. But then, of course, you've also got, you're ignorant and choose to be ignorant. So you've got your flat earthers, you've got your CERN is the demonic portal to hell, that sort of stuff. But I think you're never going to change those people's minds. But the reality is there's a lot of people who are open to learn, and they just need to be educated. And I think what you're doing, I think, is taking a big step forward, which is important.
If I might interject, it's really important for science communicators to realize exactly what you just said. Sometimes you're going to get into a fight with somebody online, and that person obviously willfully doesn't want to come to any kind of agreement. They've got an axe to grind, and you need to realize that you are never, ever going to change that person's mind. But if you are a science communicator with some audience, remember that there are, for every person you're speaking to, there are hundreds or thousands of people watching that conversation, trying to decide who they should listen to. And so you shouldn't be a real jerk, no matter how much you want to be, but you should be mindful mostly of the side audience, because those are the people you're reaching. And so that's my advice for any upcoming science communicator. Don't, accept that you're not going to win with a guy, whoever it is, and somehow it's always a guy. But the audience, you want them on your side.
I want to give you an opportunity to share some advice. I want to first target science teachers. I know that you have a bit of a soft spot for the science teachers who are particularly working hard, and in the States, particularly with the struggle with COVID and so forth. What advice would you give to that struggling science teacher as they continue to try to teach physics to their students?
Oh, gosh. I mean, I'm not... When I teach college students, and the rules are a certain way. But high school teachers are saints. That's all I can say. They're saints. And they work under impossible conditions. They don't get the credit they deserve. They don't get the respect they deserve. As a rule, I am awed by them. I'm not worthy to even talk to them. My advice to them, because they right now they've got to deal with Zoom classes and kids not paying attention and so forth. And I don't have any answers for that. But we will come out of that. And, I think the advice is the same as it always is, that there are students who really want to learn and students that don't. And it's very hard, I think, to motivate the ones that don't. But that's what high school teachers do, and God bless them. That's I do particle physics. Teaching 15-year-olds is way too hard for me.
I think what you just said is already encouraging for those educators watching to know that that you place higher value than often society does on science educators, and I'm sure that science teachers listening to that will have a smile on their face by your comments. What about the students? So let's say we have students who are thinking about a career in science, who are a bit curious, but obviously there is, they need encouragement to go the right direction, I guess. What advice would you give to them if they want to pursue a career in science?
Okay, so that I have a more informed answer. Now, this is different for every country. And so the advice I'm going to give is perhaps a little American-centric because I am most familiar with that. And you will have to, whoever's listening to this will have to adjust this to take into account their country. The first thing to remember is if you want to be a scientist, there are very few science jobs, and that's just a sad reality. And so it's not unusual for a person to go all the way through the university, all the way through grad school, and have difficulty finding a job, finding the research job that they're shooting for. And so if you want to do that, you have to start asking yourself when you're very young, when you are in high school, what is it that I can do to increase my odds, to make it that I have a better chance of getting a research position? One of the unfortunate and slightly ugly truths about academia is that there are groups that are favored and groups that are not favored. And by groups, I don't mean demographic groups. I mean universities. So if you go, say in the US, and this is by no means an exclusive group, but if you go to Harvard, Princeton, Caltech, Yale, Stanford, Berkeley, I could say some others, the faculty there are well connected with each other. And so if you come out of graduate school with a PhD from one of those universities, that already is probably a ×2 or ×3 improvement in your career prospects. Now, so that's important. That's my biggest advice is when you get your graduate degree, when you are shooting for your doctorate, go to the most prestigious graduate school that you can get into and will succeed at. And it should be a name that you recognize. And if you can have a major professor, a supervisor who has some fame, either at least nationally or internationally, this will help you. And it shouldn't be that way, but it just is. Academia is a little bit snobby in this regard. Now, the next step down, luckily, is not as bad. So where you do your undergraduate, your bachelor's degree, matters a lot less. But what you do is as an undergraduate is you should be thinking about how I can manipulate my academic career so that I have a good chance of getting into one of those high-end graduate schools. And so it doesn't really matter if you go to a small liberal arts school or if you go to a large university. It doesn't matter a tremendous amount if you go to a US school or a European school or some other place overseas. But it is important that you get good grades. It's also important that you do a little bit of research as an undergraduate. So you should find a major professor when you are your second year, third year of university, and go do research with them. Now, this doesn't have to be amazing research. You don't have to find, the next big particle or whatever. But if you do that research, your resume will look attractive. You will have skills that will make the graduate schools look at you and say, I want this student as opposed to this other student who has very good grades, but has shown no indication of being an effective researcher, whether it be a theoretical researcher or an experimental researcher. So that's really important. And then for a person who's younger than that, someone who's still in high school, my only advice there is to pick a university, or in the US we have colleges, which are a little bit different, to pick a place at which you can thrive. And when you go there, make sure you ask the question, what sort of research do the students do? Are students able to work as research assistants when they are in their second year of university? If the university or the college that you go to says, well, we don't really do very much, or if they say they do something that's just obviously really not at all interesting, then you should reconsider where you go. And then finally, just get into college. You should be good, when you're a young person, take your math seriously, take your science seriously. And this is something that some scientists struggle with. Take your English seriously, whether if you're from an English-speaking country, because you will be judged on your ability to write grants and write papers and so forth, and you should be good at it. And if you do not come from an English-speaking country, America is, ironically, the lingua franca of science these days. When I go to CERN, people may speak in whatever their language when they walk among their peer groups, but in the meetings, it's English. So English is crucial. So this is very strong advice for a high school student. Science, math, and English.
Excellent. My final question, Don, is a question that is a little bit more sharing about yourself. So the question is there something you would like to share with us, teach us of another side of you, maybe nothing to do with science, that you're particularly passionate about? A friend of mine basically used the term, something you're nerding about. Do you have something to share with us?
I focus a lot. I'm so passionate about science communication that I spend an awful lot of time on that. But I admit that I have a sneaky sort of dirty little secret that I love science fiction movies and so forth. And they're not real, but they're trashy and they're fun. I have recently watched a show called The Expanse, and if people haven't seen it, I strongly recommend it. It's a world in which all of the astronomy, all of the space technology is actually real. I mean, they eventually encounter something from an advanced technology that is different. But the things that humans do are things that humans really will do. So, so that's, I think, my real, I like to watch, trashy science fiction stories on the movies whenever I get a chance.
Star Wars or Star Trek?
Star Trek? I love Star Trek. Oh my gosh. I am, I do not own, a pair of Spock ears. I can do that. I absolutely dearly love Star Trek. My family roll their eyes, when I say, well, we could watch Next Gen one more time, and they go. No, I love Star Trek totally.
And since we're on Star Trek, who's your favorite captain?
That's a tough one. I like Picard because he just seemed so cool. Like never flustered. I mean, I like Kirk because he had that sort of devil may care, take a risk, and he always got it right. But the reality is, people who take risks don't always get it right. And then, of course, there's the two Kirks. There's the Shatner and the oh my gosh,
Chris. Chris. Yeah, I know you mean. I'm a mental blank here, but yes, the new Kirk. Yeah.
Right, and he's just a little too devil may care. So, yeah, I think in the end, I'd have to say Picard.
Favorite too. An exemplar leader, I think, in many ways. I read a book called Make It So. I'm not sure if you've heard of it, but it's actually a business leadership book, but it uses Jean-Luc Picard as a tale of how to lead an organization or lead a team and so forth. So an excellent book. So.
But have you seen Picard, the show Picard?
I have indeed.
I've only seen the first season, and I was very sad.
I was too.
I mean, it was such a letdown. You go from Next Gen Picard to the next. Is the second season any better?
I haven't actually started watching the second season, but yes, it was. Yes, having said that, it seemed a little bit haphazard. There wasn't the sense of the Picard of old. In that regard, he's become old and dottery, but then again, he is 25 years older. So
it's true. I also find that I'm looking forward to Discovery when it comes back. I finished watching that. I'm caught up to date on that. I like that as well. That's been I like it in one respect better than things like Next Generation. For Next Generation, the episode usually comes back to the beginning, so there's really no change. There's no evolution of the plot line. Whereas in like Deep Space Nine, each episode things changed, and so with Discovery things changed, and I'm enjoying that one as well.
Well, Don, thank you so much for your time. I really appreciate you taking your time out, and I certainly hope you continue success at Fermilab. And continue to watch your videos. I'm sure as many other people who are watching continue to be looking forward to your zany t-shirts, your excellent physics, and your regular, and I would agree, much beneficial dad jokes thrown in between.
Well, thank you very much for having me.
Well, I hope you enjoyed this episode. Please subscribe to get notifications of up-and-coming interviews as well as my other physics content. My name is Paul from Physics High. Till next time.